Welcome to Compressor Starting Problems. My name is Jerry Myron with RectorSeal. We are going to do an overview. We're going to review conventional 3-wire hard start devices and components, a review of 2-wire hard start technology, comparing 3-wire versus 2-wire devices in real-world testing, competitive technologies, and how to do a true run capacitor test. What are hard start kits? It's a mechanical potential relay connected to a start capacitor that is wired into the compressor to aid in compressor starting. Why are hard start kits needed? Low supply of voltage, poor quality of power supply, inadequate or undersized wiring, pressure differential at start, multiple units running and starting at once on the same grid, and times of peak energy usage. We also find older compressors that need help starting as well. It can be related to one of these issues or internal issues within the compressor. Understanding counter EMF, the counter electromotive force, is understanding the basic concept of opposing polarity through a magnetic field. That is, the counter EMF or back EMF is in opposition to the moving field that created it. When power is applied to the run winding, the rotor turns and generates the counter or back EMF to the start winding. Actually, the counter EMF is generated through all the windings. So now that we have counter EMF across the run and start windings, we have total EMF across the run and start terminals. All electric motors possess the properties of an electric generator. Now let's review conventional 3-wire hard start kits, devices, and components. Standard wiring, the traditional hard start kit 3-wire assemblies. They've been used since the 1930s. It uses a potential relay and start capacitor with dedicated wires, dedicated locations. Every major compressor manufacturer that utilizes or offers a 3-wire hard start kit utilizes the 3-wire as their standard. The 3-wire design. Here's a picture of a Train XL20i high efficiency unit. The 3-wire design is made up of a potential relay that is connected between the common and start in series with the run capacitor. The entire series is in parallel with the run capacitor, causing this circuit to be in series with the start winding. This is key. So let's take a look at a 3-wire hard start schematic. It's been used in the AC mechanical refrigeration systems like I said, since the 1930s. And with this type of assembly, we have 3 wires that are dedicated, meaning each wire has one and only one place within the circuit in which it can be correctly connected. We have a potential relay connected between the start and common. So the traditional way to read counter or back EMF is between the start and the common. But the traditional way requires matching the exact pickup and drop off voltages between the motor and compressor. And those voltages, the requirements are going to vary by only tens of volts. Let's go back to the wiring schematic and see how the 3-wire hard start kit works. We have a potential relay, a coil connected between the common and start or across the start winding. The closed contacts of the potential relay are in series with the start capacitor. All this is in parallel with the run capacitor, or a whole entire circuit is in series with the start winding. Now the motor is off and running. This is a good hard start kit. How does it work? When we apply power to the run winding of the compressor, the motor turns very slowly, struggling to get started. The speed of the rotor is measured by the amplitude of the voltage generated, or the counter EMF. As the motor generates a certain RPM, the motor generates the counter EMF. Engineers use EMF because this is the voltage at the source of the voltage. As the motor generates counter EMF, the amplitude of that voltage is directly proportional to the speed of the rotor. We determine the rotor's RPM by the voltage generated. Calibration of a potential relay is such that at 75% of the rotor's full speed, voltage is high enough that we can pick up the contacts in the potential relay to take the start capacitor out of the circuit. This is a good hard start kit. The problem with 3-wire hard start kit is you need a different relay with differing pickup voltage, dropout voltage, continuous impulse voltage, response time voltage, All of these specifications vary within different compressors. As you can see on this chart, this is a Copeland handbook that has 64 different potential relays. This is an old chart. Now Copeland has up to 102 different potential relays that have to be utilized in a three-wire connection. Why is that? The compressor manufacturer, they manufacture and design a compressor. They take their specs to the motor manufacturer. It's there that the compressor manufacturer specifies the voltage, the torque, the horsepower, efficiency, temperature rise of the winding, and so forth. The one thing not specified is the voltage across these components. When they start the motor, they measure the voltage, they determine that this particular compressor will require this specific potential relay for that specific motor. And the next time they design a compressor, they have to go through the same process again to determine the correct start components. And like I said, motor manufacturers have 102 relays to choose from. It's unlikely that HVAC techs carry a full line of relays. That's a huge burden of inventory, and that is what precipitated Fritz Schroeder, the inventor of Kickstart, to come up with the two-wire design. So capacitor, potential relay variations. It's unlikely that the techs carry a full line of relays, like I said. It's a huge burden, different configurations for start, run, relay capacitors. The one of the things that is specified in the motor's design is the voltage between start and run. When engineers design motors, the voltage between start and run on all two-pole PSC motors, permanent split capacitor motors, is in a very narrow window. That's because that voltage is specified and consistent. So let's look at the Copeland handbook when it had 64 different potential relays, whereas the voltage between start and common, and this is for all three-wire combinations, the voltage is all over the board. The first column is the Copeland part number. The second column is the pickup volts. That's the voltage that potential relay is to take the start capacitor out of circuit. Then you have the dropout voltage and continuous voltage. So will that first relay that has 320 to 340 pickup voltage that is required to take the start capacitor out? The dropout is 60 to 140 and continuous is 395. If the potential relay for the first one works, will it work for this second column Copeland part number? That requires a pickup voltage to take the start capacitor out between 150 and 160. And as a distributor, you sell potential relays that are all over the board, just like this. Those are specific for the three-wire combinations. So the voltage variance specification, the voltage is specified between start and run when that motor is designed in order to match the run capacitor requirements. The voltage between start and common, it varies by hundreds of volts and can only pick up within about a 10 to 20 volt range. So whereas the voltage between start and run terminal is consistent and varies by only tens of volts, why? Because the start and run terminal voltage variation, that is what's specified by the engineers in the design process. Now let's take a look at the two-wire hard start kickstart technology. So how the two-wire system was founded. If that is the case, and all two-pole PSC motors have basically the same EMF between start and run, then why don't we just take the potential relay and coil and connect it between start and run terminals rather than at start and common? Maybe now we can cover all the applications for two-pole PSC motors with just one potential relay. Let's get back to the schematic. We determined that when power is applied to the run winding, the rotor turns and generates a back EMF. And I keep stressing this because we're going to see real-life testing, and you can see how this works. This is key. It generates a back or counter EMF through all the windings, not just through the start winding. So now that we have back EMF across the run winding and start winding, we have total EMF across the start and run terminals. So let's take a wire from the common terminal and move it over to the run terminal. You'll have a diagram that looks like this. We disconnect the start lead, move it to the left side of the run capacitor, then take the wire from the potential relay and move it to the run capacitor. So we redraw the wiring without changing it electronically. It's where we are picking up the back EMF. So finally, we take the run winding wire, move it to the run cap, and you now have a schematic that looks like this. We haven't changed anything electrically. We just redrew the schematic. More importantly, we now narrowed the back EMF is always going to be the same in this two-wire connection coming off of the run capacitor. So the kickstart way to read back EMF, it was a patented design. This was after much time of Fritz Schroeder, the inventor, going to the motor manufacturer, going to the compressor manufacturer, building a lab, testing all those compressors that this particular manufacturer had, and confirming, is this how it's always designed? It's always the same between start and run. They said yes. And they said he just couldn't get to the patent office fast enough after all of that was confirmed. Now, locked rotor amps, another key component when we start looking at these charts that are coming up. Locked rotor amps or locked rotor current, that is the amount of energy needed to begin the motion of the rotor within an electric motor. And obviously the locked rotor amps, locked rotor current is much greater than full load running amps because of the power required to operate the equipment attached to the electric motor during startup as well. So the locked rotor amps can be as much as 600 to 800% the normal full load amps, depending on the motor. Let's look at the real life testing. Here we have a compressor with no hard start kit. On the left column of the chart, those are the amps. On the bottom, milliseconds. So you can see from 0 to 600 milliseconds, 0.6 of a second. This is critical. All of that data, using that data acquisition that can be captured 5,000 measurements per second. We captured when a motor starts up to see what is actually happening inside the compressor. Here's what we have. The 230 volts of locked rotor amp and pressure is equalized at 140 pounds per square inch in gauge. What we see here is voltage across the start and run terminals. The gold line, that is the counter or back EMF. The voltage that's generated by the rotor across the start and run terminals. The green line is the locked rotor current or locked rotor amps, what you would see in an oscilloscope. Now you can see that the voltage line is still low to about 180 milliseconds because the rotor has not started turning it enough to generate the back EMF. As the motor is starting to turn, the increasing counter EMF in gold is driving the locked rotor current down. So by the time we get to 200 milliseconds, the compressor is running at full speed. The slide depicts the forces at play inside the electric motor. The gold line is the counter EMF. The green line is the locked rotor current or locked rotor amps, and the black line is the rotation of the rotor. So when we add power, you can see the back EMF in gold. In green, this is the locked rotor current. The rotor is starting to turn, having a hard time to get started. At about 120 milliseconds, the rotor has made one turn, and that's where I circled the red circle to generate. It started to generate some counter EMF. And the locked rotor current in green is going down. At 2.5 turns, the locked rotor amp is down. The motor is up and running. All 2-pole PSC motors require around 2.5 turns to reach full speed, regardless of the voltage or load applied. So with this motor's max RPM at 3,500, it generates 600 RPM at the first rotation, and 1,950 RPMs at the second rotation, and finally reaching 30 RPMs by the third rotation. Let's look at factory type 3-wire hard start kits versus a 2-wire kickstart in real world testing. This chart shows a compressor with a factory hard start kit. It's a 3-ton recip compressor, 187 volts to the unit, an ARI condition in which they test compressors. Note that the pressures are not equalized. We have 90 pounds suction and 280 pounds discharge. The red is the start winding current. Look how long that locked rotor amp is in the circuit, over 100 amps up to about 610 milliseconds. Let's compare that. And again, this is a factory hard start kit with 145 microfarad start capacitor. Let's compare that to that same compressor, same conditions with a kickstart T05. The kickstart T05 has 189 microfarad, and the same suction, the same discharge, and it takes about 150 milliseconds for the system to get up and running. So what does this tell us? The difference between the two. If you look at those charts and you see the red, the start winding current, the longer that is in the system, the hotter those windings get. We're going to talk about burnout on compressors and how damaging that is. The sooner you get that out, the quicker, the better it is, the less heat generated to that compressor windings. But we're also illustrating that the factory did supply a hard start kit, but on those units where they do have supplied hard start kits, they're going to use one that is most cost effective, most affordable. Whereas a kickstart has a much more robust start capacitor at 189 microfarad versus 145 microfarad start capacitor. What about scroll compressors? Here's a Copeland scroll hard start kit comparison. A Copeland scroll, many people say scrolls don't need a hard start kit. Well, this particular scroll has 197 volts to the unit, no hard start kit. That same system with the Kickstart KS1. Between the two, the run winding is staying in the circuit, back EMF is trying to be generated, and the start winding, it just really did not help much at all. And it is in the system for about 450 milliseconds. Whereas a Kickstart got that Copeland scroll up right at 1/10 of a second, 100 milliseconds. Now we're talking about the heat. The longer that start winding is in the system, the run winding is staying very active, trying to get the compressor up and running. That is unnecessary heat. So a compressor manufacturer years ago gave us what they had for warranty claims. Out of 100 compressors that were returned, 78 that were defective out of 100 compressor returns. Why were they defective? The majority of them, as we show here, it's because of the start winding burnout. Heat is what kills these compressors. So we're going to look at some more charts, and just keep in mind, the quicker you get that unit up and running, and when it gets it up and running, a mechanical potential relay, it always takes the start capacitor out based on the back EMF it reads at 75% of full speed. So now let's look at competitor technologies. PTCR, positive temperature coefficient resistors. Just talk about the Curie point, the Curie temperature, the temperature at which a certain magnetic materials undergo a sharp change in their magnetic properties. That is the temperature at which PTCR discs can no longer conduct electricities. So how does that apply to the hard start kits? The PTCR discs must heat to 248 degrees Fahrenheit to choke off the start capacitor. Compare that with hard start kits with a potential relay. The potential relay is necessary to take out that start capacitor based on the back EMF and the pickup voltage when that, at the precise moment that motor is at 75% of full speed. But a potential relay also has a drop-off voltage in which the contacts are closed, so the start cap can be ready to start again. Whereas PTCR discs do not have the ability to utilize start cap with dropout voltage. Rather, they have to cool down to 115 degrees to reset. But while the compressor is running, when the PTCR discs took out the start capacitor, electricity, while the unit's running, electricity is still heating, keeping those PTCR discs hot. It's when the unit shuts off that those discs are no longer receiving electricity. They must cool down to 115 degrees before it can take out the start capacitor again, before it, for a lack of a better word, drop off voltage, or perhaps for the contacts to close again to utilize a start capacitor again. It's just not likely in the much warmer climates. Remember, an OEM approved potential relay takes a start cap out at the precise moment, regardless of what the voltage is, if it's 187 or 197 or 220 volts, 230 volts to that condensing unit. Well, then the back EMF, the time or the in which the rotor builds up the back EMF, the counter EMF. The potential relay will always take the start capacitor only when it reaches 75% of full speed, whereas timing devices or electronic devices are always preset at a certain time. So if it's less than desirable voltage, then the start capacitor may not engage or be taken out in time. Or if it's perfectly ideal conditions, then maybe it's going to be in too long. But it is not operating how the manufacturers want it, utilizing potential relays that read the back EMF to take it out at 75% of full speed. So let's look at the three different products. The first one, Copeland, 197 volt, a PTCR with capacitor. And we can see the duration is up to about 750 durations. One compressor manufacturer told us anything longer than a half a second, than 500 milliseconds, is getting those windings up to about 2000 degrees. So you can note that that start winding in red is in the circuit long after the compressor is off and running. That's undue heat. Now here we have one with an electronic timing devices that is utilizing a start capacitor with 88 to 106 microfarad. Whereas using on that same Copeland compressor, utilizing a Kickstart T05 or a matched factory 3-wire kit, that means using the exact potential relay that is required and the start capacitor designed, or the Kickstart T05. And this is how long, based on reading the back EMF, just over a 50 milliseconds, 1/2 of a tenth of a second, compared to the timing device, up to 6/10 of a second. Now there is another competitive product, a so-called universal 3-wire kits. In a 3-wire design, it's impossible to make a universal hard start kit using a 3-wire connection. Let's take a look at that Copeland handbook again. It has 64 potential relays. One potential relay in that competitor's product cannot replace all 64 potential relays in a 3-wire configuration. So let's take a look. Let's peel back on those three. The competitor's product has 3 part numbers, but they're only utilizing 2 potential relays. In the 3-wire combination, you see the pickup voltage of the one on the left is 180 to 195. The dropout voltage, 40 to 105. Then you see the one on the right has a pickup of 162 to 165 volts. The pickup voltage that will take the start capacitor out, 180, the other one is 162, with a window of about 15 volts. If we go to that chart, these are the units in which those hard start kits will work, looking at the pickup voltage, the dropout voltage, and continuous voltage. So this works on less than 10% of relays on all Copeland compressors. Whereas the Kickstart, the potential relay, is reading the back EMF between start and run. That's the 2-wire technology. 3-wire, it has us to read the back EMF between start and common, and the voltage is all over the place. Whereas with you can have one device with a permanent split capacitor, single phase compressor on all these units, it works. Now let's just talk about using the wrong relay. There's a Copeland scroll, wrong potential relay. The potential relay picks up too soon. It picks up before the compressor is up to full speed, which is about the time the power was applied. So in this instance, the hard start kit might not even have been installed, because of this product's potential relay used in this instance has a pickup voltage too high for the unit. So the start cap was not taken out of circuit. On that same Copeland scroll unit, 197 volts is being applied using the 2-wire Kickstart KS1 or using the OEM approved start capacitor potential relay, it takes the system out, it takes the start capacitor out of circuit just over a tenth of a second. So let's consider the wrong components again. Of all those defective compressors, the majority of those compressors that were defective, the start winding had burned out. Now let's look at another important thing, the true run capacitor test. This is very important, is how to conduct or how to test the run capacitor, because frankly, that is what the kickstart is connected to. 2 wires, non-dedicated wires, but it is connected to the run capacitor. It's important to test the run capacitor while the system is running. Fritz had seen where a lot of the kickstarts for a time were being returned or were failing. They were blowing up. That's because there was a bad batch of run capacitors years ago, which apparently is not the case now, but run capacitors do lose power over time. And when they do, let's say it's supposed to be 60 microfarad. This is to test exactly what that run capacitor is operating at. And if you take the amp draw, you multiply that times 2654, you divide that by the applied voltage, and it's 50.2. That's the actual microfarad that run capacitor is running at. But if you look at the label and it says it's supposed to be at 60, then that is outside the 7 to 10% window that is allowed, which means that power is now shifting over to the potential relay. The potential relay is supposed to pick up, but now it's starting to chatter. It's not opening completely, and then eventually it's just going to weld shut, keeping the start capacitor in circuit. That was what was causing the damage. The only thing that can cause a kickstart to fail were failed run capacitors. And since run capacitor is so inexpensive, we recommend to change the run capacitor, consider changing, know what that run capacitor is before you take a kickstart to it. We also have available a chart. This chart has already done the math for the contractors. You can use the applied voltage, the capacitor's amp draw. Let's say the capacitor amp draw is 7. You look at the very top row, and it's 370 applied voltage. Then we can see measuring it while the system's running is at 50 microfarad. Now you need to confirm what that run capacitor is supposed to be at. It's kind of like when you do a stress test, you want to test your heart under load. There's a lot of things going on with the run capacitor. You want to test it under load while it's running and not just shut the system off and test it with your meter, a 9-volt meter. The kickstart models, we have T05, the maximum torque for all reciprocating scroll and rotary compressors 1 to 3 ton. The KS1, maximum torque for all reciprocating scroll and rotary compressors 3.5 to 5 ton. So summary, heat kills the start windings. Kickstart does not generate heat buildup. It minimizes the time in which that start capacitor is in the circuit. PTCR and timing or electronic devices do not work consistently, and a universal 3-wire only meets a subset of applications. The correct potential relay and start capacitors reduces damages to compressors. Always test your run capacitor and test the run capacitor while it's under load. This is Jerry Myron. If you have any questions, you can email me at jerry.myron@rectorseal.com. Thank you for your time.